Hello everyone. Hello everyone. And now it's time to start Dotnetos week. So today we have the very first day and the very special guest. So a few words about the initiative before we go to the main part, which is the presentation. So Dotnetos week is our initiative, and all initiatives require some support. So we have some partners that helped us to provide the content that you will see during the whole week. So we have KMD and Demand Technology Center as our sponsors, so that helps us to organize all this. So thank you for them. And also, what about our week? We have today Maoni Stephens, which will introduce herself. So I will not speak a lot about that, but we have other speakers, like we have Martin Hoppe, which will speak tomorrow. During Wednesday, we will have a discussion panel about .NET in general. So it seems also to be a very nice thing for you. Then we have Sebastian Solnica that will describe some stuff related to debugging or other low-level stuff. And the whole week will be ended and closed by Stephen Taub, which probably, I hope you know him. So it seems that we will have a very nice week, and each evening, at least evening in Europe, will be about .NET and stuff that we love in .NET. So stay tuned with us, stay tuned with the whole thing, and do not forget about all these films and all these meetings. Just subscribe to our channel so you'll be informed about everything that is going on here, because we plan to do other interesting stuff. So having said all that, now I would like to take all the slides from me and let's introduce Maoni, which is just she just waken up because in USA it is pretty early. So hello Maoni. You are muted, so you need to.
Right. Okay, now it's unmuted. All right, cool.
It's super cool to have you. It's super cool that you agreed to provide us a talk today. It is not super cool that it is online, not in Warsaw as we planned, but maybe next year we will see. So I'm just here as a background. Maybe you can just start talking your presentation and introduce a few words about you. I will just give you the whole scene with your slides and I'm just going out.
All right, okay, so we'll get started then. Okay. All right, let's see. I need to. Okay. So today we're going to be talking about pinning, as the title suggests. Another goal of my talk was I wanted to take this opportunity to also just explain some internals in the runtime, because a few weeks back I did a mini survey where I asked folks, what did you want to hear in a conference talk that's online now? So internals seem to get the most votes. So we'll take this opportunity to talk about internals. First, all right. So we'll go through some basics of pinning. I mean, basics are pretty simple. You all know what pinning is. It's to tell the GC to not move an object, right? Very simple concept. And how to pin, from the user code's perspective, I will, sorry, I'm having a little bit of a technical difficulty here. So yeah, so how to pin, we have two ways, right? And we have a fixed keyword that you can use, and you can also create a GC handle and give it the pin type that will tell the GC that whatever object that this handle points to needs to be pinned. If you're in the runtime, of course, you have more ways, right? It's a lot more flexible if you're in the runtime. You could just tell the GC directly that you want to pin. But from the user code perspective, these are the two ways that you can pin an object. So let's talk about some fundamentals of pinning. So first of all, how does the GC discover an object is pinned? Notice that when we said, what is pinning, we specifically mentioned that pinning is to make the GC aware that this object is pinned. So it sounds like this only really matters to the GC. So how does the GC discover that it needs to pin an object? Well, as most of you know, that we have different phases in a GC. So mark phase happens first, and we start from what we call the user roots, right? By the way, throughout the slides, I put links to various documents that you can go look at later if you need more details on these. So user roots means that stack variables, right? GC handles and finalized queue. These are what is provided to the GC to start market with, right? So we call them user roots. And these roots can then report a managed object. So what happens in the runtime is GC starts and GC will ask everybody, do you have any objects for me to mark or to start market with? So these roots will report to the GC an object that GC will start with. And when it does this reporting, it can tell the GC various things about this object, right? So there's a parameter actually called flags. So various runtime components can set different flags when it reports things to the GC. One of the flags, as you can imagine, is pinned flag. So when GC gets reported an object and sees that the pinned flag is on, it then knows that I should not move this object, right? What GC does is it sets a bit on the object header to indicate that this object should be pinned. And then later in the plan phase, we'll check this bit. But wait, what is the plan phase? Right, so as I mentioned, I will take this opportunity to talk about some details. So this is one such example. The plan phase is not a term that you see often in the literature. I think this is a pretty specific term to RGC. So the plan phase is a phase that simulates a compact phase. And the goal of the plan phase is after the simulation, without actually moving the objects, we calculate a number that tells us whether compaction would be worthwhile, right? As you know, the compaction is, doing a compacting GC is more expensive than doing a sweeping GC, right? Sweeping GCs do not move the objects. So we want to make sure that if we are going to do all that work to move objects around, it's actually going to be worth our work, right? So what this means is that we calculate where we would move the objects to if we're going to compact. So, and plan phase goes through the condemned portion of the heap. So for those of you who are not familiar with the term condemned, I know some people find it quite funny that we use the word condemned in the GC literature. That this just means the generation or generations that are getting collected. So let's say you induce the GC yourself and you tell the GC, I want to induce a Gen 1 GC. Then the condemned portion of the heap in this case means Gen 0 and Gen 1. It always means the generation that we tell you that we're collecting plus all its younger generation or generations, right? So that's very important, this condemned portion. As I have observed that most people know that we have a generational GC, right? If you ask a lot of, especially the perf folks, right? Perf engineers, what sort of GC the .NET has, most of them would tell you we have, they're aware of the generational part. However, I have observed that very, very rarely would I actually see somebody care about this generational aspect of the GC when they do a performance analysis. So I want to really emphasize on this generational aspect. I have a short video that's about what does being a generational GC imply. I see there's a typo, it should be a generational GC. So you can feel free to go watch that afterwards. So the generational aspect, what does it mean? It actually applies to all phases of the GC, as you could imagine. I mean, for something that doesn't collect the whole heap most of the time, right? As you probably observed that we don't do full GCs very often, which means we don't actually collect the whole heap very often. And that's completely by design as a generational GC. So for a lot of the performance analysis, it's actually the right approach to focus on the condemned part of the heap, not the whole part, right? This is a really key concept that I've been talking about in various documents and blogs and videos. So we just mentioned root reporting in the mark phase. So some of the root reporting is generational. So for example, the handle table that reports the GC handles to the GC, that is organized in the generational fashion. So when a Gen 1 GC asks the handle table to please report me your roots, the handle table would report only the Gen 1 and Gen 0 handles. I mean, the specific detail is not as simple as it sounds. There's cases where we have to reduce a group of handles' age in order to compensate for the youngest generation in this group of handles, but that's kind of beyond the scope of this talk. So handles are generational, but for example, stack is not. So when we ask the stack walker to report its roots to us, the stack walker just reports all the roots it knows about, right? However, it will be filtered as soon as it comes into the GC. Because as soon as a root is reported to the GC will look at the object that root points to, and then decide, or if I'm doing a Gen 1 GC, is it actually in Gen 0 or Gen 1? If it's not in Gen 0 or Gen 1, then I don't care about it, right? So GC does nothing with this object after that point, which makes sense if you think about it, because if we're not collecting Gen 2, right? If we're doing a Gen 1 GC, which means we're only touching the Gen 0 and Gen 1 part of the heap. If we're not collecting Gen 2, that means Gen 2 objects are all alive and they will not move for sure, right? So it makes sense. So getting back to the plan phase, which we were talking about, there are two bits that are set by the mark phase that are checked by the plan phase. One is a mark bit, the other one is a pin bit. So the mark bit, you can imagine that just as an object should be live. For each of such objects, the pinned bit may or may not be on, depending on the reporting, right? So when it encounters a pinned object, it would record some info about this pinned object on a side data structure, which is called the pinned queue. And then what we do is when we need to calculate the relocate address of something, we know that we should not be calculating anything for the pinned object because the pinned object by design will not move. However, there's another concept I wanted to introduce, which is the plan phase actually, it doesn't operate on objects, right? So far I've been talking about objects, but the plan phase actually operates on plugs. It's the phase that constructs plugs from objects. And now let's talk more about plugs. So what is a plug? Well, a plug, put it simply, is an adjacent group of live objects, right? So after the mark phase, we know exactly which objects should be live in the condemned portion, and their mark bits would be on. And then if we discover a group of adjacent live objects, those will be formed into a plug. And the space in between two plugs is called a gap. This is also explained in this short video I made, and you can find more implementation details of plugs in Conrad's book. So why did we do this? Why did we not operate on objects, from this point on in a GC? Well, plugs were invented for performance reasons. We can calculate the reloc address on a plug instead of on an object, which is a lot faster because a plug could have many objects. And another really dramatic advantage that we get is we can take advantage of the spaces, of the dead spaces, the gaps in between plugs. So to store the reloc address and some other info. So this means that we don't we don't need any additional space to store information about reloc address and others, right? We just need to store that information right in front of a plug, which is the gap for that plug. However, as I mentioned, for pinned objects, we have special handling. which requires us to use a bit of additional memory. Okay. So now let's talk about the consequences of chain this. So it does have a limitation, which is each object that belongs to its plug will have some implications on this plug. For example, the pinned object would make the plug that contains it a pinned plug, right? Because since we're operating on plugs, that means we can't really treat each object specially. Well, we used to not to do this. So I'm talking about the history of how we handled pinning. So we used to just treat a pinned plug that contains a pinned object, the whole thing as a pinned plug, right? And what is the perf consequence of this? Well, so most people, I think, that I've worked with, they know about the heap size implication, right? Because GC cannot move these pinned objects / plugs. It means, well, it can't really just squeeze all the dead spaces out like we normally do with a non-pinned plug, right? However, I like to point out something that perhaps is less clear to many people who work on perfect investigation. So we do compact plugs, right? The non-pinned plugs in between the pinned plugs. Like we have to, right? Otherwise, the heap would just, as soon as you start having pinning, the heap would just grow easily out of bounds. So we do have, if we have this picture, right? So I have a NP means non-pin plug, then there's pin plug. So non-pin plugs are throughout the slide deck is denoted by the light purple color, and the pin plugs are dark purple. So if we have this picture, right, this is what we see in the plan phase. We've formed a bunch of plugs, and I'm using this outer rectangle to, you can think of it as a segment, right? If you don't know what a segment is, you think of it as a large chunk of memory that we reserve and use as a unit of the memory that GC uses. So this could be on 64-bit, this could be very large. It could be more than 1 gig or more if you have server GC, right? On 32-bit, this is a lot smaller. Regardless, this is a segment, and when we see this picture, we know that the end of what we call the end of segment, which really just means the end of the last live object on the segment, is here, right? So this is before we do anything. We just merely discovered that we have these live objects, and some of them are pinned. And now let's calculate where they would be moved to if we were going to move them. Okay. So now you see this picture. So MP1, we looked and we discovered that it can be compacted into the gap before the first pin plug. And NP2 will not fit. We don't have enough space anymore. So it would fit right after the first pin plug. So as you can see, we still have some free spaces, right? The white part in the picture is what we call free spaces. So we still have some after the compaction, or if we were going to compact because of the pin plugs, right? Sorry. So now the end of segment would be moved back. Right, so when we talk about compaction, we all on the same segment, we always compact to the lower parts, the lower address parts, right? So now the end of segment would be moved lower in the address space. So as you can see, the heap can then become fragmented because of the pin plugs, right? But if we think about this, yes, it's easy to see that the heap can be fragmented, but how fragmented? So we already established that pinned objects, they're limited to user roots, right? You can only declare an object is pinned via one of the user roots mechanism. And yes, as I mentioned, in the runtime, you can also be more flexible and report other pinned objects to the GC. But the point is, they're only limited to reported objects, right? What we call the root objects. In other words, if I just have an object on the heap, right, and it has some references to some other objects, there isn't anything that we can do to say like this reference is pinned, right? Meaning the object that this reference points to is pinned. There isn't such a mechanism, which means the number of pinned objects are really limited to the reported ones, right? So compared to the number of possible objects on the heap, this number is quite small, right? If we look at the heap, GC heaps these days, it's easily, you see millions and millions of objects, but you don't have millions of reported root objects. Well, okay, like sometimes people do go a little crazy with the GC handles, as I've observed. I have started to see like the number of handles in the hundreds of thousands range, which is I would encourage you not to do if you can help it. But the point there is that you don't see people having like hundreds of thousands of pinned handles, right? A lot of these other handles are due to other handle types, not pinned. So at the end of the day, we could say like the number of pinned objects is just not that large compared to the number of total objects on your heap, right? So does that mean we don't have a problem if there aren't too many pins? Well, let's take a look at a picture, right? So even if we don't have too many pins, they can still be scattered, which means this, right? So I have this one picture where the end of segment is where the arrow points to, right? So this is the same picture from the previous slide, yeah. And if we have a slightly different picture, it's just that the second pin plug is a bit further back on the segment. So as you can see now, it's introduced a much larger fragmentation than the first case, right? So this is why that when you see the guidelines for performance with regard to pinned objects, you often see that people suggest that you should pin a batch of them instead of just one at a time. In fact, our own implementations in the .NET framework, some of them do this. When they need an additional pinned object, they would actually allocate like 16 of them, something like that. So they would pin the batch, which means that it's very likely that all of them would end up in one pin plug. And they also try to do this early. The reason for doing this early is because imagine that in a simple case, it's perhaps not very realistic, but in a simple case, you could predict exactly how many pinned objects you would need during the lifetime of your process. And you would allocate all of them and pin them at the very, as soon as you can when the process starts up. What this means is, obviously, these objects would survive, right? Which means they would be in Gen 2. Let's leave out the large object heap for now, where it's not really relevant for explaining this. So they'll all be in Gen 2. And most of the objects that we know in Gen 2 are also long-lived. And if they're not long-lived, they would, we would have taken advantage of the free spaces in Gen 2 and compacted some of the Gen 1 survivors in there. And that means that your pinned objects would stay in a very compacted portion of Gen 2, which means they don't really move, which also means that they don't really introduce any fragmentation problem, right? So that's why you see this guideline on pinned objects. Now, as I mentioned, that these days I really try to concentrate on the generational aspect of RGC, and pinning is, of course, one of them. So the first point that we realize is we compact the whole heap very infrequently, right? And as I mentioned, that's totally by design, right? The generational GC's idea is that we don't need to compact the whole heap very frequently. We just do much shorter ephemeral GCs instead. So what this means is, this is actually something that two people asked me recently. So this is a very prevalent kind of concept that people often overlook. So what really matters is what GC sees in the condemned generations, right? which means that, if you do Gen 0 and Gen 1 GCs most of the time, you need to look at the number for the pinned objects for those GCs. You don't open up a heap snapshot and look at how many total pinned objects I have, right? Because it just doesn't really matter for you most of the time. So what matters is what GC sees in the portions that actually handles in that GC. And if the GC doesn't observe pinning, it's as if that you didn't pin anything, right? It's just, it's, if you could manage, like, again, I'm going to give you a very simplified example that is not realistic, but illustrates the idea, right? Let's say you observe your GC, once every 10 seconds, right? On server GC, it's quite common to not do a GC all that often. So if you could manage to pin something in between those two GCs, in that 10 seconds, then GC doesn't know about it at all. It doesn't care about the fact that you pinned something, right? So this means we often want to focus on the ephemeral collections pinned, the observation on the pinned objects from those collections. And one common case that GC would actually or might actually trigger compacting for GCs is when you run into high memory load situation, right? So let's talk about that first before we talk about the ephemeral case. So what is high memory load situation? So I have a link here that explicitly explains what this means. For this talk, we can just say when you run into very high physical memory load, then GC will treat that as a high memory load situation. It would be more aggressive about doing full block and GC, right? So pinning, first of all, would make estimating how much work, or how much space we can shrink the heap by harder, right? Imagine if we didn't have pinning at all, then we should know exactly how much we can shrink the heap by, because we know how many objects they survived, we know the size, and we can just, slide them, right? GC does what we call sliding compaction. So GC can just slide them toward the lower address space, and we should know exactly how much we then free up at the end of the segment, right? However, pinning makes this harder. And what makes it harder is that we can't really predict the pinning situation, right? In GC, one of the tuning philosophies that we've been going by is that we use the history to sort of predict the future, right? This is very common to do, that you observe what's been happening or what happened recently, and you sort of use that as your guideline in tuning for the next GC, right? But and we, this is a very effective tuning thing to do. However, it doesn't necessarily mean that we can handle all the situations where things change pretty dramatically, right? So because we can't really predict how this tuning situation would change, we can only be so effective in calculating the tuning parameters when it comes to this high memory situation, right? So we could end up triggering full block and GCs quite often. So what happens in GC is when we start GC, right, one of the very first things that we do is to decide what generation we should be collecting for this GC, right? And if it's Gen 2 GC, we would decide whether this should be done as a block in Gen 2 or as a background Gen 2, right? Background Gen 2 would be done mostly concurrently, so we can let the user threads go pretty quickly. So if we are in this step where we're trying to decide which generation we should actually be collecting, one of the factors that we take into consideration, obviously, is a memory load, right? So basically, we don't check the memory load for every GC. Like, for example, the Gen 0 GC, we treat it as a very local thing, right? Because Gen 0 is supposed to be a very small part of the heap. So we don't believe that Gen 0 can change the heap enough that would change your memory situation much at all. So we don't go and check if we should do full block in GC in every GC. But we do check it very often, right? Every time we do a Gen 1, we decide that we would need to do at least a Gen 1 GC, we would end up checking whether we should escalate this GC to a Gen 2 or not. So in the high memory load situation, it's actually quite often, as soon as we detect that, the heap seems to be in a situation where doing a full block in GC would be productive, we tend to get into that situation pretty often. Because the idea is that if there's no pinning, and if we did a full block in GC, I mean, in this case, it means we would be doing a compacting GC, right? If we did a compacting GC, our hope is that the heap would be reduced by a lot, then you wouldn't be in this high memory situation anymore. Unfortunately, with pinning, that's not necessarily the case, right? With pinning, because we don't actually decommit the gaps in between the pin plugs, we could end up with a situation where we did do a compacting GC, but the total memory used by the heap didn't change a lot. So then soon after, we could get into the situation again. I mean, in GC, there's also tuning that we do that would combat the situation. But the point is that we might make the decision that we need to collect the full heap pretty often in this situation. So obviously, I'm going to talk about what we do to combat the situation. So previously, this is what we have. So after Gen 2, we have this picture, right? So we have some, the pretty large gap actually in between the last two plugs, right? And then soon after this GC, we might detect we do have enough fragmentation in Gen 2, right? Which is what causes us to want to do a full block in GC in the high memory load situation. So, and then on another GC's entry, right, we would see this picture. I should say actually mark phase, not entry, right? Because entry, we haven't even built up the plugs just yet. So the next Gen 2's mark phase would see this picture, which this is, you can see that this is basically the same as the last one, the one above it, except the second non-pin plug is larger, right? It's a bit larger. Because this kind of says that we trigger this GC a bit too early, right? Because we still got quite a bit of free space to use in between the last two plugs, but we were not able to use that, which means we're not very efficient at triggering this GCs. So that's why we introduced this mode, which I call the provisional mode. What this means is that instead of triggering GCs on the entry of the GC where we calculate which generation we should collect and all that, we actually would change our mind in the middle of a GC. So it's sort of like in this provisioned fashion, right? So we have the same picture, right? After Gen 2, we have this. And at this point, we would detect that we did do a compacting Gen 2, and we are in the high memory load situation, and we still have high fragmentation. So then we realize that, well, this high fragmentation must be due to pinning, right? Which is something that we already said that we can't really predict. And it can be a problem at this point, because at this point, since your memory usage is already so much, we really want to be careful so we don't use yet more to get into paging, right? Because as soon as you get into paging, the perf just basically tanks at that point. So at this point, we turn this provisional mode on, which means next time we do a Gen 1, which means we would do as many Gen 1s as possible to use up the free space in Gen 2 before we actually decide to do the next Gen 2. Instead of calculating what is fragmentation in Gen 2 and do a Gen 2 based on just that, right? So if we do a Gen 2 after this, we see this picture, right? So the MP prime, that's the plug that was added by this Gen 2 GC, right? And this is good. So like we have a bunch of free space in Gen 2. We're using that free space. That's exactly what we want to see. And we do that. We could be doing this for a very long time, right? Because if you had a lot of free space in Gen 2 to begin with, and you don't survive all that much from Gen 1, this free space could last us quite a few Gen 1s. And that's good. We want as many Gen 1s to happen as possible, right? And until we see a Gen 1 that actually needs to grow the Gen 2 size, right? So the end of Gen 2 right, used to be at the end of that pin plug. But now we discover that we don't have enough space to accommodate the Gen 1 survivors, which means we actually need to grow the Gen 2 size. And this is something that we don't want to see. So as soon as we detect this, which is, we haven't really grown Gen 2 by much at all at this point, because all it grew by is just however much that the Gen 2 free space couldn't fit to accommodate the Gen 1 survivors. So it's just a little bit at this point. But at this point, we then trigger a Gen 2 immediately, right? We would finish up this Gen 1. Actually, I think I just do a sweeping Gen 1 at this point because it doesn't really matter anymore because we know the next time is going to be a Gen 2. And Gen 2 will be able to reclaim much more space, right? So this means that we don't really need to predict anymore. Like we know that we're using the space as much as we can before we need to trigger the next Gen 2. So that makes it a lot more efficient at using the Gen 2 free space. So now let's talk about pinning during ephemeral GCs, right? Because as we said, that this is really important to us. So this is a picture we have before Gen 0 GC, right? So I didn't use the purple colors because we're not talking about plugs right now. And now, during the plan phase, we form some plugs, right? So we have Gen 1 start that stayed the same because, well, we're not doing a Gen 1 GC. So we know we're not going to change the Gen 1 start. And the new, we have, compacted pin plug. Let's say we're doing a compacting Gen 0 GC, right? So we have this picture. And now the new Gen 0, so first of all, now the end of segment would be where the arrow says new Gen 0 starts here, points to, right? So now we can make a decision, right? Do we want the new Gen 0 to start here or not? Because if we do, that means we actually can't take advantage of the free spaces in between the pin plug in that we already pushed into Gen 1 until next time we do a Gen 0 GC, right? Because if you allocate, you can only allocate in Gen 0. So if we do this, it means you will then allocate after the arrow. And as we can see, now you're kind of close to the end of the segment, right? So, and then, the two, the green arrows point at the free spaces that we couldn't use until next time we do a GC. So that's not really a good situation because if we have free spaces, we want to use it as soon as possible, right? Instead of having to do all this other work in order to use it. So now, if we make a different decision at this point, right, in the plan phase, we could say, let's actually start a new Gen 0 here, right? Because we know that we have free spaces to use in this case. And then this gets into what we call demotion, right? Demotion means that essentially we're saying that we're demoting these two pin plugs, right? Because these two pin plugs, they were supposed to end up in Gen 1, but now they're not in Gen 1, they're in Gen 0. So their generation actually got reduced, right? So this is what we call a demotion. So if we have the new Gen 0 starts here, right, then we can, appears that I accidentally missed that I should have some blue parts in between the new Gen 0 start and the first pin plug. So pretend that part is blue. Right. So then after another Gen 0 GC, we might have this picture, right? So again, we did demotion on the two pin plugs. And, but however, you can see the new Gen 0 start here, that arrow got pushed back a little bit because we did survive something from the Gen 0, right? So now there's a bit more stuff in Gen 1. And Gen 0 still starts before the first pin plug. So we can actually use the spaces where in between those pin plugs and the Gen 0 start, right? So now let's ask ourselves, is our problem then solved, right? This looks like, if you pretend that white part between the Gen 0 start and the first pin plug also blue, we're using the space really efficiently, right? So is our problem solved? Well, we see that these two pin plugs, they keep getting demoted, right? What if these pin plugs are really big and they stay for many Gen 0 GCs? This could happen, right? If you have async IO, which is like perhaps the most common situation where we would introduce pinned objects. They could be, you know, as long as your request is still there, it's not finished yet, the pin plugs or pinned objects are still there. So these pin plugs could stay there for many Gen 0 GCs. And this was actually a real problem, right? This was not theoretical. Like I was seeing this really often. Like this is what exactly caused the ephemeral collection time to be longer than it should be, right? Because, so if we go back to here, let's say these pin plugs are quite big. When we demote them, it means we need to look at them every time we do a GC, right? Because they're in Gen 0, and Gen 0 is always collected. I mean, which is not completely true, but yeah, let's say for block and GC purpose, they're always collected, right? So this means if I have very long, very large pin plug, I would need to handle that pin plug in each GC, and that's not a good situation, right? Because we already established the generational aspect, which says that we actually don't want to handle all that much of the heap each time. But this means that we'd have to at least handle these pin plugs all the time, every time we do a GC, right? So this is where I introduced the POPO feature. POPO stands for Promote Only Pinned Objects. So for the first time in the .NET GC history, we actually broke a plug apart, right? So far, or up until that point, every time we form a plug, the plug, that plug always stayed as one plug. Like we never broke that plug because like so much of the GC is operating on the concept of plug. Breaking it up would mean to change all those other phases that rely on plugs. And that was a very difficult thing to do, but it did yield very significant perf benefits, right? So we had first-party customers where we did this feature, we tried this feature on, and it reduced their ephemeral GC collection time by a whole lot. So I'm going to talk some of the details of that. I mean, it's totally out of the scope to talk in very much depth, but I will mention some of the reasons why this was difficult, right? So the idea is you break this one plug that we used to call a pin plug into 2 or 3 plugs, and so make each one look like a normal plug, right? So I have this plug that I used to just be completely dark purple, which meant they're in one pin plug, but now I'm going to break this up into 3 plugs. I said 2 or 3 because you could imagine that maybe the pinned object is the very last one in this plug. So in that case, we only need to break it into 2 plugs, right? So what we do is we actually create these artificial gaps in order to break them apart into plugs, right? Because as we said, that gaps are what was in between 2 plugs, right? So we create these we create these artificial gaps. Notice that for object B, the gap is actually created right before the object after B, right? Because I can't really carve out part of the pinned object and modify it, because by design, that pinned object could still be used during the GC, right? The other objects are fine. Like other objects, we know that you're not, GC is free to move them. But when you pin something, you're telling GC specifically that because one of the most prominent situations where you would pin to interop with native code, right? So you're telling us like, I'm going to use this object while the GC is going on. So I can't actually carve out part of the pinned object. So I made a compromise. So I carve out the object right after it, if there is one, right? As I mentioned, that there might not be one. If it's the very last one, then we don't care about this second gap, because we would already have a gap naturally. So then we would then form this into 3 plugs, right? So now we can say the first and the third plug, they're non-pinned, they're not pinned. So we're free to move them. And then the one in the middle is called a pinned plug, right? So this is this looks kind of simple, but in reality, this was very hard to handle because each phase, and as I mentioned, that many phases in GC do care about the plug concept because they operate on plugs, not objects. So they need to recognize this, and they recognize them very differently. So for example, in the plan phase, right, we know that we still need to calculate the reloc address on the actual length of a plug, not this, the plug that we just made up, because we need to be able to fit the whole A and the whole B somewhere. Obviously, we can't just fit A minus that gap size, right? So when we ask to calculate the reloc address, it's still on the actual length, right? In the relocation phase, we also had to do something different, which was, such as, if you look at a plug, we need to realize that the first plug in our picture is right before a pinned plug, and the third plug in our picture is right after a pinned plug, because we need to handle these artificial gaps specially, right? Fortunately, in the way that we handle plugs, it makes it very natural for us to recognize the plug right before and right after it. So we can communicate information between those three plugs, right? So that's how we handle that in reloc phase. In the compact phase, there's also complications, as in when we want to copy objects, we better copy the whole A and the whole B, right? So we would temporarily recover these artificial gaps, and then we would copy the whole object or whole plug, the non-pinned plugs over. But we have to recover it because the next plug compaction would need the information that we stored in the artificial gap. So it's that was a lot of work to implement. So we also need to record the information we overwrite with artificial gaps, obviously. But let's think about another scenario, which is, what if A or B is too small, right? What if A is only as big as an artificial gap? By the way, when I say artificial gap, I should make clear that this artificial gap is the size of the min object, right, which is 3-pointer size. But A could be 3-pointer size, right? Why not, right? So how do you handle that situation? So, then we had to record what we call the short object in this case and handle them specially. So anyways, I'm going to stop here for the reasons, because this would take a lot more time to explain if we want to get into the, in details. But as we can see, I can also see I'm kind of over, so I'll try to finish this up quickly. So the root cause of all these perf issues is because we have no control over which objects get pinned, right? This was a decision that we made, or I didn't, because that was before my time, but this was a decision that was made at the beginning of the .NET runtime, that you can pin any object that already got allocated. So, this was made at the time for performance reasons to make interop fast. But as you can see, that later on, we had to do a ton of work to compensate for this, to make it fast, right? So this means that we cannot break this contract. I can't, next version of .NET, I can't really say you can no longer pin objects that already got allocated. It just doesn't work. However, we could provide a mechanism to help the users with this situation, which is, if you actually have control over the objects that you pin, for example, you can control when you allocate them. And as we have seen, it's actually quite common that people would actually pin the objects as soon as they allocate them, right? This is very common in the I/O handling, and people tend to have a buffer of a pool of buffers that they allocate, and they just pin them right away. So in .NET 5, we introduced this new feature called the pinned object heap, right? So this is exactly for the situation where you will pin objects that when you allocate them, right? The high-level idea is like they would then stay on their own segments, so they don't sort of contaminate, everybody else. And they're also swept, obviously not compacted because we know we cannot move them. They're swept in Gen 2 GCs. We don't really need to sweep them that often because, as I mentioned, there just aren't that many objects that you pin compared to the total number of objects. So a Gen 2 GC frequency is frequent enough. So that's all I wanted to say today about pinning. And if you want to connect with me to get more GC resources, I highly, highly recommend you to read this document that I just wrote a few weeks back that I published in a GitHub repo. So if you have suggestions to change it, feel free to submit PRs. My blog, and I also recently started this YouTube channel where I put some short videos where I explain the GC. You might want to go take a look at that. And on Twitter, you can also ask me questions, which people do. But I have to say that I don't look at Twitter constantly like some of my coworkers do. So if you post a question, it may be an unknown amount of time before I look at Twitter next. Sometimes I look at it pretty often, especially when I post stuff. I mostly use Twitter to post stuff. So when I post things, that's when I look at Twitter pretty often to see, if people have feedback on it. And if you happen to ask me questions during that time, obviously I would see it and answer it right away. But sometimes I may not look at Twitter for like a few days or a week. And then, of course, as a last resort, if you have an issue where it requires us to really put in time to investigate something for you, the best way for that is to actually file an issue on our runtime repo. So that concludes my talk for the day. And I think this is where the question answers start.
Right. Thank you, Maoni, for an awesome talk with awesome amount of details. So now the part for the questions for you. So if you have any question, still there is a time. We have one question from Azet Brainiac, which was, I believe, when you were just describing fragmentation in general in the fundamentals part. So
it's kind of fragmentation with pin plugs independently on. Is this, what, I don't actually understand what this means.
I believe we can rephrase this question as a concern about the difference between fragmentation between SOH and LOH in general.
Yeah, right. So on large object heap, of course, large object heap, as you know, is not compacted by default. However, in .NET 3.1, I actually started compacting it if you're running in a container scenario. Right, meaning that if you are running your process in a memory constrained environment, so if you put it in a container but you don't specify a memory limit, it doesn't count as a container scenario for the GC, right? However, if you do specify a memory limit, you can do this in Linux with C groups or on Windows with a job object. If you do assign a memory limit on container, we do compact large object heap automatically. So what we used to say for years and years that if you pin something on the large object heap, it had no effect, it's no longer true, right? So in a container, constraint scenario, that it is true that when you pin something on a large object heap. So from that perspective, now pinning on a large object heap is a lot more similar to pinning on a small object heap, right?
But you fortunately always stated that do not rely on this implementation detail that
right. We always say that. Yeah, I believe everywhere we give the advice, we always make sure that we said do not rely on this implementation detail.
Exactly. Yeah. But so there are special conditions when this compaction of large object heap is happening, like you said, the hard limit. But anything more to add?
No, it's mostly just hard limit. If hard limit is on, then we basically look at the fragmentation in large object heap and compare to like the whole heap size and all that. So we do some calculation there if it's over our threshold. I believe I used the total fragmentation in large object heap, compare it with large object heap size, and compare it with the total heap size. Because maybe your large object is really prominent on your heap. So even when the fragmentation ratio isn't that high, it's still worthwhile to compact it. So then we would also compact it out in that case. Yeah.
And I believe the decision was because you are not so afraid of compacting large object heap in this scenario because you expect it is not so big, right? So it is more beneficial to compact it.
You'd be surprised like how big limit people specify on these containers. But I totally get what you're saying. Like when you talk about containers, at least the chance of having smaller heap is higher now. Right, because people always talk about like, oh, I want to put a really small memory limit on my container. However, that's not always the case. I've come across customer scenarios where they put like gigs of limit on the container.
But I'm saying that because this is an obvious risk. I can introduce quite huge pauses.
Of course.
Yeah. So, okay. Yep. The next question was from Hasnik. I believe it is one of our colleagues from Poland, but I'm not sure. The question was the very popular question, like every time someone is describing the whole complexity of pinning, the very first question is why there is no special place for pinned objects if they require so many complexity. But as I showed, he is aware of a pinned objective already, but the question is why it was not introduced earlier.
Yeah. So yeah, the reason was really that pinning is a very user-facing feature, right? Unlike many of the features in the GC where you don't actually see it, I mean, just happens automatically when it needs to. Pinning is something that you can control. So in the GC, one of the policies that we have is like, if it's something that the user can control, then sometimes we can view that as you can implement some sort of code changes on your side, right? So this is not something that you have to rely on GC to happen. Like often we have seen that we, obviously as a runtime team, we also have the freedom to go change, sort of higher level libraries above us, right? So we did actually exactly that. In the past, we have gone and changed like, the HTTP implementation to allocate the pins more efficiently. And we saw a big improvement from that. So over the years, we didn't want to have to ask the users to change the way they coded, right? So that's, I believe that's, you could say like we're being very considerate to the users, but I also believe that providing them with more options is also nice, right? For the users that wish to put in a bit more work to make code changes, it's nice when they have an option. So it was a feature that we had been talking about for years. Like I remember, I don't know, 10 years ago, there's already requests or people ask me like, why don't you just put them all in one portion of the heap? But because this is something that the user does have some control over, and we do have some control over, we just didn't do that feature until, very recently. So it's not because we're not aware of it.
Yeah. And you have this new keyword as a contract, so there was no flag for pinned boolean or something like that.
And as I mentioned, and as I mentioned, some people can't actually use this feature because they do not control when they allocate the objects, right? So it's not like this feature is it will solve all our pinning problems. We still, like over the years, pinning is one area that I really, we really had to do a lot of work on. And I think we're now with the combination of the pinned object heap, we're at a good situation. But, before we had Popo, that was kind of a pretty big headache, right? When I looked at people's profiles, sometimes I was like, I really wish we could break up the plugs there. And so that's what we made.
Right. Yeah. So for the very first time, we have an API, which is called gc.allocate array, which is just a new way of allocating stuff. For the beginning of the .NET, as far as I believe. By the way, do you plan to add allocate object or something like to have a flag for pinned single objects?
Yeah, so I've been thinking about, as I've been telling various folks who asked me the same question, I have been contemplating on asking for a new. Right, so because the reason why I didn't provide an allocate object is because then array is very simple, right? You specify element type, you specify the length, that you're done. But objects is a different story, and we've done a lot of work over the years to optimize the object allocation code path, right? So I don't really want to throw all that away. Like if you have a very simple object that you just want to put additional attribute on, like pinned or whatnot, right? It would be kind of a shame if we just threw away all the optimizations that made this object allocation code path very, very fast. We just threw all that away, and just so that you could call the allocate object API. So I was thinking that maybe we could talk to the compiler folks that they can provide a new operator, so that would allow us to specify these attributes that you can currently specify with allocate array on. So.
Right. Pinned new will be quite nice.
Yeah.
Keyword.
Yeah.
Okay. As the next question is from Azet Brainiak again. As far as I remember, it was when we were describing provisional mode.
Yes. So Gen 2, normally when you don't do a Gen 2 GC, right? Let's say we do a Gen 1 GC, we already fill the free spaces with Gen 1 survivors, right? But in the provisional mode, that is exactly what we're trying to do as much as we can until we can't anymore, right? Because we don't want to get into a situation where we keep doing these Gen 2 GCs only to discover that we actually are still having a lot of free spaces in Gen 2, right? So we try to do as many Gen 1 GCs. And by the way, Gen 1 GCs are the only chance that we have in order to use the free space in Gen 2, right? So the free space in one generation can only be used by the survivors of its younger generation. In Gen 0, that means, your user allocation doesn't exactly have a generation, but we'll just say like Gen 0's younger generation is a user allocation, right? Which means that when you allocate in your code, when you do new something in your code, you would be using the Gen 0 free space. And in the same, along the same line, we can say that when you allocate or when you survive something in Gen 0, you would be allocating into Gen 1. And you would be, if Gen 1 has free space, you would be allocating into those free spaces, right? So normally Gen 1 GCs are already filling in the free spaces in Gen 2. It's just like the reason why we have this provisional mode is because normally we may not do as many Gen 1s to fill the free spaces enough due to our other tuning decisions, right? Because as I mentioned, if you're in a high memory load situation, we tend to be very aggressive at doing full GCs because we really, really want to get the heap size down. So we really don't want you to get into a paging situation because that's just kind of terrible, right? So we try very hard there, but without the provisional mode, you could be doing Gen 2s too early, which is exactly what provisional mode is trying to avoid. So you would see, so the pattern of GCs that you would see in this case is without provisional mode, you could be doing like Gen 0, Gen 1, Gen 2, Gen 0, Gen 1, Gen 2. Let's say you do it in the 1-1-1 ratio, which is really, really high for Gen 2, right? We definitely normally don't want to see like a 1-to-1 Gen 1 to Gen 0 ratio. Actually, I believe this actually doesn't happen because, as I mentioned, we also have other tuning to combat that situation. But the point is that you could see a Gen 2 pretty soon after some Gen 1s. With provisional mode, we're saying we're going to do the most number of Gen 1s until we know that Gen 1 survivors cannot fit into the Gen 2 free spaces anymore. So we make sure that we use it absolutely to the fullest. So we sort of like with the provisional mode, we get the best of both worlds, right? We use Gen 2 space very efficiently, but we also don't delay our Gen 2 too much, or we actually really just don't delay it at all. We just do it when we know that we need to do one. So we don't trigger as many full blocking GCs. So that's the idea.
Awesome. Thank you. Okay, the question, which is kind of organizational one, which is about links, as
Yeah.
we will
Can I
organize
give
that.
you the, like, where can
Yes,
I publish the,
we
yeah,
will
I
we
can,
will publish it
definitely.
for sure. We will publish it in the description above the link above the recording. So
Yeah.
also you can find
I
it
can
there.
also just publish this, like maybe in my, I don't know, maybe in my memdoc repo or something. So people can
We will
get it.
find out the reason, the way
Yeah.
for you not to need to type the links, but have it available as the whole
Yep.
presentation.
Yeah, for sure. We'll make this
Another
available.
question is there any documentation around pinned plugs and non-pinned plugs?
Yeah, you can look at Conrad's book.
Right. As far as I
Yeah.
know, yeah.
Yeah. So
Maybe you know
if you
another.
want some sorry, go ahead.
No,
Yeah.
sorry.
So if your book already mentions, in the chapter that talks about collections specifically, right? You already talked about like pinned, how we break them apart. But I just want to mention more like why we did, because we didn't do this before, right? By the time you wrote the book, we were already doing it, but this was not what was in the GC before, like years before now. So I also just want to mention like not just the implementation, but also like the challenges why it made it so difficult to actually break up plugs. So, but if you want implementation details, you can look at the chapter in Conrad's book. That would
Right.
be we don't have document. I mean, so my opinion on such implementation detailed things is that if you just want to know about it because you're curious, like in general, like I mean, thanks for writing the book, by the way, because now I can just refer people to your book if they want to know about some implementation details. So you can, there's already that resource. If you actually want to do work on it, then I personally believe that you just have to, dip your toes in the code. There's no other substitute ways, right? You must be able to debug the GC under debugger, and no amount of documentation would really help you there. So yeah, so I view it as, so please go read the book. And if you still have questions and if you're seriously thinking of doing work on it, then please put the GC under debugger. That's really the best way to learn about the GC code.
Absolutely. I spent a lot of hours debugging also this part
I
because
bet.
it was
Yeah.
totally undocumented, and I was really
Yeah.
impressed by the level of complexity, all these pre-plugs being
Yeah.
stored, and
Yeah.
it's really, really nice.
One of the first things I did when I joined I was gonna say when I joined the GC team, but really when I joined, I was the only dev. So the last dev essentially handed me over the torch. So that's basically what I did. I just used a very, very simple test that just, allocated temporary objects. I just put it on a debugger and I just debugged the hell out of it. So that's how I learned.
There is a lot of functions to be debugged. Okay. Yeah. Other differences regarding pinning when running inside the container. You mentioned compaction of the large object heap, which somehow yes is related to pinning.
There's not, so with the container scenario, I actually try to make it look like there's not. I try to reduce the difference from the GC's perspective to handle container or not. They should be very similar. So the main difference really is how the GC recognizes like the memory, how much memory it can use, and how it calculates the memory load. Right. So before, if you're running standalone, if you don't have a memory limit, when we talk about high memory load or situation, what I meant is, we take the amount of physical memory, total physical memory on the machine, right? You take how much is actually in use, you divide those two numbers, you get a number. That's what we call the high memory load, right? It's in the percentage. However, when you're running inside a container, you no longer have, with a memory limit, you no longer have access to the whole memory on the machine, right? So then we take how much memory that you have access to, and we treat that as a total physical memory has. And then we calculate like how much so one thing I should mention is that we calculate how much physical memory your object is using, sorry, your process is using, and we divide that by the total amount of memory that you have access to in your container. We treat that as the memory load. What this means is that if you have multiple processes and they're all very active in the same container, it may not work very optimally. However, that's a problem that I've seen people have even without the GC in the picture, because all memory managers have the same problem. Because we don't really have a way to, I mean, strictly speaking, we could go enumerate all the other processes in the same container and calculate memory load that way, but we don't do that currently. I mean, maybe if this, as I understand, a lot of folks that when they run something in the container, they tend to only have one process or one dominant process in a container, right? Because the task of managing multiple active processes in the same container is just, it's not easy. So because they're already doing that, which also means that we haven't had all that much motivation to go and do the work to enumerate all the other processes, right? So currently it's best if you just have one dominant process in the container. But that's the main difference, that how we view the memory.
Awesome. Related question is about how do you detect whether you are running in the container from the GC perspective or from the runtime perspective?
Yeah. So we do have a get memory info API, right, which was introduced in .NET 3, but I sort of beefed it up by a lot in .NET 5. So even the version in .NET 3, it already tells you how much memory GC thinks it has access to. So if you, it doesn't really tell you like, you know, this is under a container, but it does tell you how much memory GC thinks it has access to, which means that if you know that your machine, I mean, you can always do whatever you want to get the total number of, the total amount of physical memory on the machine, right? So there's APIs to do that. And you can do that if you compare with the total amount of memory that GC has access to. If the latter is a smaller number, then you know that you're running in a memory constrained scenario, which is what we call a container scenario, right? Because it's not, as I mentioned, you know, when we're running in a container, we try to make it look like it's not very different, because it makes things much easier, right? We don't want to have all sorts of different code paths to say like, oh, you know, you're in a container and we have to care about something differently. We try to do that as little as possible. So GC will be told like, I have this much memory I can work with, and that's it. So GC does report that to you. So if you want to know that if your GC is only using a subset of the memory, then you could use that API to figure out.
Awesome. Okay, next question, the last one as currently,
Yes.
about pinning with our IO methods and async.
Yes, right. The async IO is perhaps the most prevalent case for pinning. And yes, it is implemented in the framework itself. So over the years, we try to reduce the amount of pinning code that, as a user of the framework, for you to write as little as possible, right? We try to have you write that code as little as possible. So we try to reduce it as much as possible. So nowadays, like usually if you're using the framework, right? If you're working in the framework, it's a different story. But if you're a user of framework, you tend to write very, very little code that actually pins something. However, under the covers, if you need to interrupt with the IO or with native code in general, we do pin stuff under the covers, right? That's sort of like what pinning was designed for. So if you want to see like how many async IO you have going on, you could go, there's a couple ways you can get that. One is you can go to SOS and do the GC handles command, which lists async pinned as one of the types it reports. So those async pinned means that you have the async IO. That's what caused the async pinned handles to be created. I believe if you take a heap snapshot in PerfView, and look at the roots, right? The async pinned handles is also reported as one of the kinds of roots.
Okay. By the way, do you plan to use pinned object heap for that, or just stay with the current?
So pinned that my plan is we will so in .NET 5 there's already code that was modified in the framework to use the pinned object heap. But my plan is to check to see in the in the next version, or hopefully next version. In the next version, we'll check the framework code and to see like how much of that we can convert to use in pinned object heap. Sort of the same kind of exercise that we did back then. When I mentioned that we did modify the framework before to allocate pinned objects more efficiently, right? So we could do the same thing and go and search for such scenarios, which I believe there's definitely still some in .NET Core, and we can change those. So that is the plan.
One question just arises now in my head about the allocation speed in while pinned object heap, whether there's use any kind of allocation context, or it is just synchronized between threads, like
allocation on the pinned object heap is done basically in the same way as large object heap.
Okay.
So as you know that for large object heap and small object heap, they each have their own lock for allocating on it, right? So pinned object heap also has it shares the same lock as large object heap.
So
and which means that well, I mean, it's the same overhead as allocating a large object heap, right? You can think of pinned object heap basically from the allocation perspective. It just has the same characteristics as large object heap.
Okay. Yeah. So we have a question related to that. Are allocate array and allocate uninitialized array are the only ways now to put something on pinned object?
Yes, that is the only way from the user code to put something on a pinned object heap. Yeah. And as you already mentioned, that we don't have allocate objects today. Yeah. So hopefully that will come at some point as a new. But the reason why I don't have an allocate object today is just because, as I said, allocate array, especially because if you look at the patterns where people would get into the pinning situation, it's mostly arrays, right? It's mostly you allocate a buffer that you use. It's like mostly actually byte arrays. So that's why we chose to only provide the allocate array for now. But yes, I'm definitely thinking about how we can provide an allocate a normal object or non-array object for you without losing much perf optimizations that we did. So.
Right. Okay, we don't have any more questions regarding one from Sebastian about maybe next time we will just make I have one question for you, just from me, not from the attendees. Like, what other use cases of pinning have you seen in your experience? Not about besides native code cooperation. Do you have meet any other? Because you said also that it is most prominent use cases for pinning was designed for cooperation with native code, but maybe you have met any other interesting use cases that people are using it for, I don't know.
Most of the cases I've seen are around native. It's just a matter of like how much people use it for. I have seen people where you can always you always have the choice on your side, which is why I said pinning is very user-facing feature. So some people they choose to pin, some people choose to copy, right? So like that copying is always an option, right? In fact, as you know that like Java doesn't have pinning, so you do copy, and so what I've seen is like how much people choose between the two routes, right? How much they decide to pin, how much versus they decide to copy. I have come across folks who just pin the hell out of it because they didn't need to interrupt with native code a lot, which actually turned out to not be that productive. Because I think one thing is because they didn't really understand the generational aspect. That's why I try to talk about it so much these days, because what they did was they pinned a lot of objects that they could have let survived into the higher generations. And then they rarely do the higher generation GCs. So to them, like the objects being pinned or not actually just didn't really matter much. But what they did was like they allocate, I think this was before I put in some other tuning changes for pins, which was like we kind of unconditionally demoted pins that we observed in Gen 0 and Gen 1. But so what ended up happening, because this was a long time ago, that they actually just hit the scenario where they would go over the same pinned objects over and over again each time they do a GC. And they really didn't have a very big, managed heap. They have a much more, much larger native heap usage, right? So what they did was like a GC that's supposed to take very, very little time ended up taking longer because we had to go through the same pin objects over and over again, and really for no good reason. So yeah, so that's why I suggested them that they actually didn't need to do all this additional work to pin something; they would perform better. So, but yeah, it's mostly related to native.
Right. Okay. Not to tire you too much. We have only 2 questions. One question from me, and I promise it will be just the end. So
Okay.
now just a thought from the Alexander that bounded channel with discard new would benefit from pinned object heap, as far as I understand, but it is, I believe, related to async IO in general using pinned object heap.
Yeah.
As far as I
What's this
remember
to
that.
start new?
I'm not sure. Maybe Alexander, you can clarify your question. I will just ask the second one, which is about manually pinning something.
No, it's you. So when you allocate something with that allocate array, you're saying that I am doing something to the array I'm asking you to allocate. So you can't really allocate something already and then pin it. That's the whole idea of doing the pinned object heap, right? So you don't pin something that you already allocated, because as soon as you allocate it, then you don't really have any idea where it's going to be on the heap, right? So that's the key is you tell us that we can pin it at the time that we're allocating it.
Right. One important thing related to this allocation on pin object heap is this limitation that you cannot allocate anything that contains references. Let's say it has to be
right.
detailed. Yeah, so
Yes.
it is important side note for folks listening to us that you
Yeah.
cannot. In fact, it has the same limitation as the pinning itself. So you cannot use anything that contains references, for example, which is good for you because you don't have to use marking there because there are no references from the pinned objective, right?
Yeah. Well, like you said, you already can't pin something with references, so we didn't feel too bad about not increasing the functionality there, but not having the the uninitialized array is more interesting in the objects with references case, right? Because we can't really afford to have uninitialized memory that contains references that GC wouldn't need to stump upon, right? Because we can't afford to just step or go look at a reference that points to some object that already got destroyed. That's why for the uninitialized array case, you absolutely cannot tell us that you also want to allocate something with references, because that means that when a background GC is marking stuff, it would go and chase down every reference that's contained in an object. If you just allocate an object that has a bunch of uninitialized memory and GC will treat those as references and then go chase them down, GC would just crash, right? So it's more for that case. For pinned, you already can't allocate stuff that's not bulletable anyway.
Right. Do you have ever considered allowing pinning something with references, or allowing references beyond the pinned objective?
So right now, if you the code that handles pinned heap, not the background GC part. If we're talking about block in GC, it could very easily handle the pinned objects with references, because there's no, all you do is, instead of not going through them for, cart marking and all that, you just do that, right? So it's just a matter of like, do we go in, step into the generation for a pinned object heap or not? By the way, the pinned object heap, it's tracked as generation 4, just like large object heap, which is tracked as generation 3. But logically speaking, right, I always talk about this from logical versus physical perspective. So physically, they are tracked differently just because we need to keep different tuning parameters on them. So we just need an array that, stores an element for large object heap and stores an element for pinned object heap. But logically speaking, they're part of Gen 2 because we only collect them with Gen 2 GCs, right? So we sort of, all we need to do in the code path that cared about, like, what generation do I need to go through? Like, for example, if we mark through cards, right, which is, for those of you who are unfamiliar with this concept, that when you do ephemeral GC, obviously you have to care about references coming from older generations into the generations that you're condemning, right? So that's, for us, that's called a cart marking. So cart marking, if you are doing, let's say, Gen 1 GC, you need to start, well, we don't, this is actually handled differently, but you can think of it as that we do both Gen 2 and Gen 3 cards, right? We need to look at the cards in Gen 2 and Gen 3 and see which ones are pointing into Gen 0 and Gen 1 range, so we can keep those objects live. It's just a matter of, like, if we allowed pinned object heap to have references, we just need to also take Gen 4 into consideration when we do card marking. So, right. Yeah.
So probably not worth for these edge cases when people need it.
Yeah.
Because if we are pinning something, probably it is passed to native code, so why references there?
Right.
Okay. Yeah. Follow up from Eric's question. He was mostly asking whether you are using begging sand, right, which is using pinning out of the.
That's why I'm saying that pinned object heap is for people who actually have the control when they can allocate, right? I mean, that's the thing. Like, that's why we need to change the framework code as well, right? So the framework can do those things that you have no control over. So the pinning, pinning is something that every time we make a change or a significant change, we do have to go through the framework code to look for cases that we can change, because this doesn't just happen automatically for the users of the framework, right? This means that, users of the GC would need to change, and that includes the framework code. So we definitely, that's one of the things on my list, that we need to go to the framework code that has control over the objects that it allocates that wants to pin. So you don't have to do that yourself.
Awesome. The very last question from Christopher. Hi, Christopher. Is there any limit in size for all those pins?
Yeah, so hi, Christoph. So if you look at, since we're open source now, you can please feel free to go look at the source if you want. So if you look at the code for allocate array, which is in gc.cs, in system.private.corelib.dl, you will see that in retail build, which obviously is what you're using, that we do not allow arrays are too small to be pinned, because when the arrays are too small, well, this is kind of a choice that we made because we're adding a bunch of overhead for the allocation path. So we don't want the allocation paths to degrade too much when you allocate through this API. So, which means that we only allow allocations once above certain size. So if you go to the array implementation, which is very simple, you'll see the limit there.
What is the limit? Or maybe the
I think we changed it to 2K.
Okay, and how it will behave if it is smaller? It will be like exception from, or
sorry?
Will be just, and what will be the behavior for those smaller arrays below the threshold?
They just don't. I think they just don't get allocated. Okay. Although let me quickly check because hello kids
Yes,
are initialized.
Christoph is also looking at the code now.
Yeah.
Okay, so slowly summing up while we are searching through the GitHub repo. We had an awesome talk with Maoni when the question took half an hour. Thank you, Maoni, for all this. Thank you for all the questions. I hope you are inspired by pinning. While pinning is has some limited edge cases, but it was awesome to hear about pinning, and people
Yeah, it
should
was very
still.
challenging to handle pinning. I
Yeah,
actually asked my predecessor, like, I was like, did you regret that we supported pinning in the runtime? Yeah, because like, if I look at the work that I had to do over the years to improve the perf, it was very significant.
This awesome complexity of the code. Always when I'm giving some workshops about internals of the GC, I'm describing here is the mark, here is the flanning, here is the compacting, but now we have pinning, and then all this next level of complexity that comes from that is just something really, really interesting and challenging. Okay, so Christoph, you will have to find those thresholds for yourself. Sorry for that. We will not keep all the people because of these questions. So thank you, Maoni, for your talk. Thank you for being with us, and hope we will meet somewhere online or maybe on site after all this craziness will end.
Yeah.
So
thank you. My pleasure.
Thank you, and have a nice day. Have a
You
nice
too.
evening, depending from where we are. Bye.
Bye.